Hello, students. I just wanted to give a brief video on the cross-section approach to finding volumes of solids. Now, what we've done in the past with volumes is basically exploited the solids of revolution. And that's a very, very useful technique. But now what we want to do is consider a situation where we actually have a solid that's not necessarily a solid of revolution. And what's going to make this particular method work is that the solid has a convenient cross section. And when I say cross section, cross sectional area. So what we want to do is just remember that for this procedure to work, at least in a method that's doable, is that the cross sections will be perpendicular to the axis that we choose for our integration. Now, I just wanted to go over a standard problem and then just summarize a couple of your WebAssign problems. But just remember, this is a very specific technique, and you can actually design solids that have these characteristics and compute their volumes. You can even make models. Now, for the first one, we want to consider a square pyramid. And so in this particular case, the base would be square. And as we move up the pyramid, the cross sections that are perpendicular to the axis of the pyramid would be squares. And so we will assume that the base area is B, uppercase B, and we will assume that the height of the pyramid is H. Now, what we want to do is prove that the volume is actually 1/3 BH. Now, what's nice about this method is that the actual formula for the computation of the volume is just a stacking method, just like thinking about stacking squares or whatever the cross-sectional area might happen to be. And all we have to do is integrate the formula for the area of the cross-section over the interval of integration. So for instance, we could have X as the independent variable, or we could have Y as the independent variable. So again, this method is very simple. And of course, it would certainly depend on how easy it is to actually construct these formulas or these functions for the area. So now in order to do the square pyramid, we simply think of constructing a triangle whose leg here is on the axis of the pyramid. And then we actually construct a leg here perpendicular to the side. And this leg will have half the distance from one edge to the second edge here. So if we assume that the edge of the base is B, we're going to take this edge to be B/2. And then of course the leg here will have length H. Now, in order to move the calculation forward, we want to also construct another right triangle here and utilize similar triangles. So I wanted you to see a picture of how we actually work the geometry. So we can move from here to here where we've got a little bit more room. So like I said before, we have the B/2 and we have the H. And then for the smaller right triangle, we just assign the leg X and the leg Y, those lengths respectively. So in order to come up with a formula for the edge, in this particular case, a formula for X, we just use similar triangles. So we'll say Y is to H, in this particular case, as X is to B/2. So basically what we're doing is taking ratios of heights and ratios of the horizontal edges. And then, of course, it's very simple to solve for X by cross multiplication, and we get B/2H times Y. Now, since this edge in this particular case is only half the distance across, we double it and we get B/H times Y. Now, that defines the edge of the cross section, which is a square. So now the area formula for the cross section will just be an edge squared. So we just square this formula and we get B² / H² times Y². So when we look back up here, this is exactly what we do. We have a of y. And then, of course, the interval of integration in this particular case will just be from 0 to h. So we will take y to lie between 0 and h, and this will be our interval of integration. And so now a very simple integral, very elegant procedure. And so we integrate from 0 to h, the b squared over h squared times y squared. And then, of course, we note that these are just constants, which we can extract, power rule, add 1, divide by the new power, and integrate from 0 to h. Now, of course, the lower limit nullifies this, so the only content that we get is from the h. And so we just get an h cubed. And now, of course, the h squared absorbs into the h cubed, leaving h, and then we have the 1/3 and the b squared. Now, of course, the b squared is simply the area of the base, which we assume to be represented by b. And so indeed, we get 1/3 bh. So this is a very elegant theorem. And of course, what you can do is vary the cross section. So you could have triangular pyramids. So what's nice about this particular method is that you have plenty of control over the development of a solid. And then, of course, you have plenty of control over the computation of its volume. Now, the other two examples I just wanted to cover fairly quickly will just be that of two of your WebAssign problems. Now, these problems are set up very simply. You don't really have to derive a formula like we did in the previous exercise. With these problems, the actual exercise gives you the base. That is, in this case, the base is the circle x squared plus y squared equal 4. So we take that region bounded by this circle. And then what is described, that is, cross sections perpendicular to the x-axis, are given. In the first case, we have equilateral triangles. And in the second case, we have semicircles. So what we can do is draw a picture of the base. That is, for this particular circle, we would see that x would run from -2 to 2. And so we just put in the edge for some particular x in this interval. And what we're noticing here, we do a lot of circular symmetry. We know that the distance from the axis to here will just be the square root of 4 minus x squared, but we have the double of the distance. So the entire distance here, or this edge, will just be 2 times the square root of 4 minus x squared. So now, what's nice is that it may have been a while since you derived the formula for the area of an equilateral triangle, but I did a little computation here, and it's very simple, just using a 30, 60, 90 triangle. And so what we see is that the area is the square root of 3 over 4 times an edge squared, or s squared. So we simply substitute the square of the edge, which we have here, that will be 4 times the quantity 4 minus x squared, times the square root of 3 over 4. The 4 is absorbed, and so we get an area formula as square root of 3 times 4 minus the quantity x squared. So now we have a very simple formula that we can integrate from -2 to 2. And now notice, our friend, we have a nice even function on a symmetric interval, so we can use our symmetry result, which we used often in the last lecture. So now we can double the result and integrate from 0 to 2, this even function. And now, of course, very simple antiderivative, 4x minus x cubed over 3, integrated from 0 to 2. Substitution of the 0 nullifies everything, but we do get content with the 2. That is, we get an 8 minus an 8/3. And of course, factor the 3, and that'll give us a 24 minus 8, which is a 16. 16 times 2 gives us 32, and we have the square root of 3 over 3 as the final factor. So the solution will be 32 times the square root of 3 divided by 3. So again, very, very useful, very, very efficient method. But again, very different from the solids of revolution. So this isn't the most important method that you'll see, but it is an interesting one. And then, of course, allows you to create any type of solid that you like, as long as you keep tabs on the actual cross-sectional area. Now, for the last example, we give the cross sections perpendicular to the x-axis to be semicircles. So now, again, when we think about the semicircles, we need a radius. And so in this particular case, the radius we can just construct from the x-axis to the curve. So our radius will be the square root of 4 minus x squared. And then, of course, using the formula for the area of a circle, we will, and of course, half of that will have pi over 2 times the square root of 4 minus x squared quantity squared. And that'll give us pi over 2 times the quantity 4 minus x squared. Now, this is our formula for the area of the cross section. So we integrate, again, as we did in the previous problem, from -2 to 2, this actual formula. But again, just like we had in the previous problem, we have a nice even function. So we'll go ahead and factor the pi over 2, but then we compensate with a factor of 2 and start the integral at 0. So again, the derivative, antiderivative looks the same. We get 4x minus x cubed over 3. We have the quantity pi because the 2's absorbed. And then, of course, we get the 8 minus 8/3 again. And then in this particular case, we're just left with the 16 times the factor pi over 3, or 16 pi over 3. So what I want to emphasize here is that the problems in and of themselves are actually fun algebraic exercises. Again, when you are given the actual cross sections, then you can compute based upon some of the relevant geometry. And we see in these cases, we were able to move the geometry forward by considering the base, just like we did in the square pyramid. So again, appreciate this particular method for its simplicity, and also appreciate it as you can develop solids that will meet your own specifications. And we are done with this. So I hope this will give you plenty of insight into working with volumes by cross sections. And we are done with this. Have a good day.